Our speakers for today are Professor Stelios Arseniadis and Professor David Leitch. Professor Arseniadis obtained his PhD from the University of Strasbourg under the guidance of Dr. Charles Mioskowski. After various postdoctoral stints in industry, Rhodia, Shirex, Boston, USA, in close collaboration with Professor Stephen L. Buchwald at MIT, and in academia, first with Professor Alan C. Spivey, Imperial College London, UK, and then with Professor Casey Nicolau, the Scripps Research Institute, USA. He started his academic career in 2005 in France as a permanent CNRS researcher and was promoted to the rank of CNRS director in 2015. The same year, he moved to the UK and joined Queen Mary University of London as a reader in organic chemistry. His group is interested in developing new synthetic methods and applying them to the synthesis of natural products and other biologically active frameworks. These methods span within the area of asymmetric transition metal catalysis, organocatalysis, photoredox catalysis, and more recently, asymmetric biohybrid catalysis. Professor Leitch obtained his BSc in 2004 and PhD in 2010 at the University of British Columbia, UBC in Vancouver. While at UBC, he worked with Professor Laurel Schaffer on organozirconium chemistry and hydroamination catalysis. He then held a postdoctoral position at McGill University, working with Professor Bruce Arntzen on the multi-component approach to building conjugated organic materials. In 2020, Professor Dave obtained an NSCRC postdoctoral fellowship to work with Professor John Burkaw and Dr. Jay Labinger at the California Institute of Technology on tandem catalysis for alkane functionalization. Professor Dave then joined GlaxoSmithKline's Catalysis Center of Excellence at Research Triangle Park, NC in 2014 and moved with the group to the Pennsylvania R&D Hub in 2015. There he became group leader of the rechristened chemical catalysis group, as well as the continuous primary group within process chemistry R&D. In 2019, Professor Dave returned home as an assistant professor at the University of Victoria in Vancouver Island. His research group is focused on mapping chemical reaction space using high throughput experimentation and developing new catalysts and catalytic reactions for complex molecular synthesis. In 2023, Professor Dave was promoted with tenure to associate professor and also received a Cottrell Scholar Award from the Research Corporation for Science Advancement. Proceeding with the talk of Professor Stelios. So I would request Professor Stelios to kindly share the slide.
Cool.
Yeah, please go ahead.
Thank you so much, ma'am. Thank you. So yeah, thanks for the kind presentation. And yeah, I'd like to thank the organizing committee, in particular Ajay, Rajesh, and Aparna. I mean, we started talking about this meeting a few months ago when I was at the NOST meeting, and I'm happy to see that we're actually doing this. It's really nice. I'd like to thank David as well because we started collaborating together for 2 years, and it's absolutely fabulous. And I also want to apologize for him because it's probably 5 o'clock in the morning there, so I'm in the right side of the world right now. So I'm so sorry for this. But yeah, so thanks a lot for inviting both of us. I mean, the idea was to talk about this beautiful project we're working on together. So before I do that, just because of the structure of this meeting, I just want to start by acknowledging a few people, and in particular my collaborators throughout since 2005, but also all the students and PhD and postdocs that have been involved in everything we've done till now. And I spent 10 years with the CNRS, and now I'm with Queen Mary. So thanks to them for trusting me. And of course, there's a few companies that have been funding our projects, and I want to emphasize particularly it's actually the same company. It's Aurel and Servier, because because they are closely involved in what we're going to talk about today, but also because they have been collaborating with my group for several years now, and it's been fantastic interaction with them. Also, just very quickly, maybe just 2 slides to tell you about what we do in the lab. So as you know, most of our work involves methodology development, and like you said now, I mean, we do a lot of catalysis, asymmetric catalysis in general, but I like to say we're very opportunistic. So if we see something unusual, we try to take advantage of it. Obviously, I spent a year with Casey, and I am attracted by natural products. It's a natural thing for us. That being said, I don't consider myself as being a natural product guy. I am more methodology driven than I actually target oriented. And we also have a few projects in medicinal chemistry. And just two projects that we're working on right now very quickly. So for the last couple of years, we've been working with fluorine chemistry, and in particular difluoromethylation chemistry. And this is something that we started initially with Sanofi. And more recently with Steve Hilton at UCL, we've been developing 3D printed reactors, photoflow reactors to run these photoredox reactions. And also another important aspect that we're working on right now is using 3D printed devices, whether they're stir bar or flow reactors that are printed with catalyst embedded within them. So this is something that we've been interested in, and we're starting to work on that. Also, another big project that has been going on for the last 10-12 years with Mike, Professor Smetana in Montpellier, and it involves DNA-based asymmetric catalysis. So the idea there is to develop a toolbox, and for any given reaction, we would design a specific DNA-based catalyst. And so, yeah, without Mike, this project would have never existed. But today I'm going to talk a lot about these guys, the work that they have done throughout their PhD, and particularly today, the work of François, Tommy, Sidonie, and Tanya. And it involves basically 2G Trost type chemistry, so palladium catalyzed allylic alkylation chemistry. So I'm not gonna spend too much time on introducing the topic. I mean, it's been, obviously we haven't invented anything. It's been known for at least half a century. So you recognize here Barry Trost and Tsuji. So unfortunately, Professor Tsuji passed away a couple of years ago. But the idea here is to catalyze an allylation reaction using an activated allyl donor, a source of palladium 0, and obviously if you have a pro-chiral nucleophile and a chiral ligand that combine to your palladium, then you can perform an enantioselective transformation and obviously generate some allylated product which are enantio enriched. Like I said, I mean, there's a lot of key players in the field, or what I like to call my role models. So you will recognize the photos here. So John, Pat, Thomas, Gilo Jones, Alakesh, who has done some beautiful work, and Brian Stoltz, and the chemistry has been applied widely in natural products. And here I depicted a few examples of complex natural products, and I've highlighted in red the specific chiral centers that have been controlled through a AAA type chemistry. What about us? So in the last 10 years, we've been heavily involved in applying AAA chemistry to various pro-chiral heterocyclic scaffolds, and so it's the case here of the succinimides, furanones, siloxypyrols, and isoxazolidinones. And the idea here, obviously, is to allylate enantioselectively and generate a quaternary stereogenic center that you can control. So in all these cases here. And more importantly, what we want to do is to use those heterocyclic scaffolds as building blocks. So as you can recognize here, these are nice precursors for alpha quaternary beta amino acids, for example. These two examples are a little bit different, and they don't involve heterocyclic scaffolds. And so this first one here, where I've represented a hydroxyphosphate, so alpha hydroxyphosphate, this was an idea we had. So we were imagining that perhaps under palladium AAA conditions, we could, so obviously have a palladium zero source that interacts with the allyl acetate, generates the pi-allyl complex and releases some acetate, and the acetate would promote a phosphor-Brook rearrangement and generate a C-centered anion. So basically transferring this phosphorus onto the oxygen, generating a C-centered anion, and then quench that anion with the chiral pi-allyl complex to generate ultimately the allylated product. So this would be an inertia-selective catalytic allylation of what we could say a compound that is readily available from any aldehydes. Unfortunately, this didn't work. So despite all our efforts, we were never able to run the C allylation, and instead we observed a complete O allylation, which sounds logical. That being said, it's actually not an easy task to perform an alkylation, or in this case, an allylation on an alpha hydroxyphosphate, because under standard alkylation conditions, the first thing that's going to happen is a phosphor-Brook. And for some reason here, in the presence of the palladium complex, it looks like there's an inhibition of the phosphor-Brook and an O allylation that occurs instead. So once again, like I said, we're very opportunistic. So we took advantage of this. We decorated the R group. We decorated the R group by various pendant olefin chains, and then we can run some ring closing metathesis and access various phosphorylated heterocyclic scaffolds of various sizes. In the case of this this substrate here, so actually this is a compound which when we started this, we didn't do our literature very well, but this is actually known as acrylonitrile alpha anion surrogate. So obviously it's not an acrylonitrile alpha anion, but it reacts like a beta keto nitrile or beta keto ester if you replace the nitrile by an ester. So you can do all the chemistry that is known around this carbon, nucleophilic carbon. And so we decided to go for some allylation, so with palladium. And once you do the C-allylated product in the presence of a source of OH minus, so KOH, sodium hydroxide, tetramethylammonium hydroxide, you can run a Ritro-Dickman fragmentation and release this thioglycolate along with the acrylonitrile in this case, or acrylate if you use the ester, the corresponding ester. And so you generate these skipped dienes, and you can work on them afterwards. We collaborated with Almec to do some biotransformations. But today, I really want to focus on butanolides and furanones. And I could tell you that obviously these motifs are present in a wide number of natural products and with various biological activities, and that is why we decided to work on this. And to be completely honest, that's not the case. Okay, what we were interested in the furanone motif for some natural product synthesis. That being said, this AAA chemistry just came to us by serendipity. The actual first reaction that was run by one of the students in Professor Cossi's group, so Candice, and she wasn't doing AAA chemistry. What she was doing instead was some Stiglitz rearrangements. So if you're familiar with the Stiglitz rearrangement, in the presence of a DMAP or a phosphine, you could do an acyl transfer. And in this case, because we have a conjugated system, so in the presence of DMAP, for example, you would transfer the acyl onto the DMAP, generate the pyridinium and the dienolate, and then you will have a transfer of the acyl group either at the alpha position or the gamma position. So Candice was interested in these motifs, and so the first one she made was the one with R prime equals H and R equals methyl. So basically, this is easily preparable starting from commercially available methyl furanone. You deprotonate with LEHMDS, quench your dienolate with allyl-chloroformate, and you get this cyclic dienyl allylic carbonate. And because she had that in hand, she was curious to try 2D Trost type chemistry. So what she did is she mixed her substrate with some palladium tetrakis in DCM at room temperature, and after a few minutes, run a TLC. The reaction was done. So she quickly evaporated the solvent and did a column. And she came back to my office with an NMR of this product, so quantitative yield to form this gamma allylated product. So we were pretty happy with that, because we were thinking that potentially if we have a substituent here at the gamma position, we would generate a quaternary center. And if we fine-tune the reaction conditions, and especially if we fine-tune the nature of the ligand, we could potentially control this center. That being said, there's one mistake that we've made in that first reaction that we didn't do a crude NMR. And when we started working on the asymmetric version, the first thing we did, of course, is to monitor the reaction, run crude NMRs, and we actually do not form this product in situ. It's actually the alpha allylated product which is formed. There is a little bit of the gamma in a ratio of 10 to 15 to 1, but it's the alpha allylated product that is formed. So now you're going to ask me, how did she manage to isolate the gamma? And so we quickly realized that when she had sorbed her crude reaction mixture into silica, we had a co-prearrangement that occurred and that transformed the alpha allylated product to the gamma allylated product. In the reaction, though, we do form the two in a 10 to 1 or 15 to 1 ratio, but we know that the gamma allylated product is not formed through a co-prearrangement, but it's formed through a competition between the alpha allylation and the gamma allylation. I'm going to come back to this in a second. Anyway, if you're careful, and if you do a very quick column, you don't let sorbent to silica, of course, you can fine-tune the reaction conditions, and you can, so this is the mechanism that is accepted, again, generating a parallel complex, decarboxylation to form the palladium dienolate, and then the difference between the normal system that you see in the literature and this one is we have a conjugated system. So in our case, we have a competition between alpha and gamma. So if we look at the results, we observe the formation of the alpha allylated product. I'm not going to go through all the examples, but basically the EEs range between 80 and 90%. But if you see here, you do form a little bit of the gamma, and the EE is 95%. And so obviously the co-prearrangement is stereospecific. So we know that the gamma allylated product is not a result of a co-prearrangement because we would have the same EE. So we were quite happy with this, and we spend a lot of time trying to change the regioselectivity of this reaction to try to favor the gamma, and we never were able to do to have that kind of result until now. So before I talk about the gamma allylation, so like I said, independently of the substitution pattern at the alpha position, we have selectivities ranging from 80 to 90%. You can isolate the compound and you can promote the co-prearrangement. And like I said, it's a stereospecific 3-3 sigmatropic rearrangement. So whatever EE you have for the alpha, you transfer. So you transfer to the gamma. So we were able to isolate the gamma allylated product in the same range of selectivity with no erosion selectivity whatsoever. And to make sure the reaction runs well independently of the substrate, we actually run it under microwave radiation for an hour at 180 degrees. Another thing that we like to do is once we have new compounds, we like to see how far we can go with them, how much structural diversity we can bring. So another thing that we tried here is to run a reduction. So, and to be completely fair with you, the idea of running a reduction here was more to reduce this butanolide to the corresponding diol, generate the mandalates, and then evaluate, determine the absolute configuration of the newly formed center depending on the ligand that is being used. And once again, we didn't do our literature very well because actually butanolides like this one are known under reduction conditions, are known to undergo this process where basically you reduce the lactone to the lactol, with the lactolate. The lactolate is in equilibrium with the open form, and the open form is at -78 degrees is much more stable. So basically, the second equivalent of diol will reduce the aldehyde, generate the alkylate enolate, and as soon as you quench your reaction, you release the aldehyde, you release the alcohol, and that spontaneously cyclizes to form the corresponding lactol. And then a PCC oxidation allows you to generate the corresponding lactone. And this is actually a nice transformation because you go from an alpha quaternary butanolide to the corresponding beta quaternary butyrolactone, and obviously with no erosion of the selectivity. And also, so we weren't able to determine the absolute configuration using the mandalates. However, we were able to transform these butanolides into two natural products, so nifurocyanuric acid and rosylaric acid, and we were able to obviously determine the absolute configuration by comparing the optical rotations of the natural and the synthetic products. So at that point, we were a little bit troubled because we couldn't, for some reason, we weren't able to put anything else than an allyl group here. So there was some limitations to the method. So one of them is to be able to introduce some diversity onto the allyl functionality. And so in order to circumvent this issue, we decided to try an intermolecular process starting from these siloxyfurans. So the reaction conditions are pretty much the same. So the same palladium source, usually palladium DBA with the same Trost ligand, and using allyl acetate as an allyl donor. And as you can see here, the result is pretty much the same. So under these conditions, we get the alpha allylated product in roughly 77-78% EE. And something that was striking, and the idea also was to be able to access a whole bunch of other natural products that have a substituent here at the 2' position of the allyl group. What we were interested in is actually replacing the allyl acetate by a metal, so introducing a substituent here at the 2' position. And when we run that reaction, we were surprised to see that the outcome is actually quasi-exclusively gamma selective, and the E's are roughly 99%. So the allylation allows you to isolate the alpha allylated product in 78% E, while the metallylation allows to generate the gamma allylated product in 99% E. And so obviously we try to look at the reaction scope, and it is applicable to pretty much anything you put at the 2' position here. So we replace it by different aliphatic and aromatic groups, and in every single case the reaction was gamma selective quasi-exclusively, and the E's were above 95% and generally around 99% EE for the gamma allylated product. So you might say this is cool. That being said, it's limited to allyl donors that have a substituent at the 2 position, and obviously you would be right. That being said, you can easily use this silylated allyl acetate and cleave this carbon silicon bond and reach the same gamma allylated product, but this time in 98% E versus 91% E. You can pretty much decorate your starting material with anything at the alpha, beta, and gamma position, which wasn't the case with the decarboxylative approach. As soon as you put a substituent at the beta position or the gamma position, the reaction worked, but the E was going down. And it was going down drastically, like 60-70% E. In this case here, independently of the substitution pattern at the alpha or beta, or as you will see in the next slide, gamma position, you always have an exclusive gamma allylation, and the E's always are over 95%. Even in the case of this non-substituted substrate at the alpha position, where in the case of the decarboxylative approach, we could never observe the single allylation, because once you allylated at the alpha position, you generated you still had an acidic proton, so it was prone to enolization and double allylation. But in this case, because we have the gamma allylation, we can easily access this compound in 97% EE. So I added these examples. As you can see here, if you have a substituent at the gamma position, you can access the quaternary center, again in 99% EE. And another example that was interesting for us is this substrate here derived from methylfuranone with methyl group here at the gamma position. And the reason why it was interesting for us is because that motif is present in a lot of natural products that you can that are isolated from various sources. And the first one that we tried to synthesize was hexacoumarine D and E. And another interesting point here is that we wanted to apply this AAA chemistry in a late stage fashion. So this is basically the last step of the reaction. And as you can see here with the standard condition with palladium DBA, the reaction works, but the yield is relatively poor. So we observed like 16% yield, although the E of the two stereoisomers are relatively high. And another series. So I'm going to come back. I'm going to come back to this in 1 second. Another natural product that we were interested in is caprolactone. So the idea here was to obviously scale up the reaction to access this methylfuranone building block, and then through a simple cross metathesis, access the natural product. So in 3 steps, 21% overall yield, 99% E. And once you've accessed caprolactone, you can easily run an epoxidation to X-carotene K, dihydroxylation to X-carotene G, or run other cross metathesis with various olefinic partners to access a whole bunch of other natural products: ferrolactone, close lactone K, indicolactone, and anisolactone. So all these natural products have been synthesized through this strategy involving a key AAA reaction followed by a cross metathesis. We also observed that this motif is present in several natural products, and those natural products are tubratolide A and tubratolide B. So I'm not going to talk about their synthesis, but it's exactly the same strategy. AAA reaction to control the center here at the gamma position, and cross metathesis to bring the side chain. So and I think this is the important part of the talk. So I really want to emphasize on the fact that AAA chemistry is actually not trivial. So I know it's been known, reported for a long time, and there are a lot of examples in the literature. That being said, it's not just mixing a palladium source and a ligand, and you have great selectivities. There are also a lot of parameters that come into play, and sometimes the reaction is a little bit capricious. And so last year, I received a phone call from Manolis, and luckily I knew Manolis. Manolis was doing his postdoc with Phil, in San Diego. And so they had finished the synthesis of cyclopamine, and so our paper came out, and they were wondering if they could use the AAA reaction to generate this motif and shorten their synthesis. And so they tried, and they couldn't reproduce the reaction. And to be fair, at that same time, we had some issues reproducing our reaction as well. So I was a little bit stressed about it. But like I told Manolis, the reaction works. We've run those reactions hundreds of times, and the reaction do work. But you really have to be careful with your conditions. You really have to be careful with your source of palladium. You really have to be careful with your source of solvent, base, etc. So it is a tricky reaction. If it's a fast reaction, you might not observe any problem. And to be fair, we didn't observe any issues for 10 years. The only issues we might have observed is maybe one time the reaction doesn't work. You just recrystallize the catalyst and the reaction works again. But sometimes, and it was the case with X-carotene, the X-carotene that I showed earlier, the reaction are much more sluggish. When the reaction are sluggish, a lot of things can happen. And so you observe a lot of side products, a lot of catalyst degradation, etc., etc. So we worked on this with Manolis, and he was able to reproduce. So don't worry, the chemistry is robust. You just need to be careful. But to come back to this slide, like I said earlier, with the standard conditions, palladium DBA with the dash phenyl trost ligand, we observed a very, very poor yield. As you can see here, we heat it a little bit. We use an excess of the siloxyfuran. These are not standard conditions. Usually the reaction will run either at room temperature or even at 0 degrees or -20. We don't use that much excess. But here the problem is that the siloxyfuran is not that stable under reaction conditions. So you hydrolyze it to the corresponding furanone. And when the reaction is sluggish, you have some reaction with the DBA, and you have a lot of things that happen. And this is when a paper came out, and this is actually when everything started with David. So a paper came out in ACS Catalysis, and all started with a phone call with David, and I was wondering. So he developed this very interesting palladium zero complex. So it's an achiral palladium zero complex, which I'm not going to go too much in detail because he will, but basically it's bench stable, solution stable. So I was wondering if I could replace palladium DBA with his DAB palladium MAH complex. So he sent us some, and indeed you can use the DAB palladium MAH complex to run your AAA reactions. And as you can see here, we have a much better selectivity observed in the synthesis of X-calculatin D and E. And you can also access X-calculatin B by simply doing an allylic oxidation. I'm done because now David is gonna talk about the rest of the projects, and I think maybe we can have the questions at the end, right?
Perfect. Well, thank you so much, Stelios, for passing the baton over to me to talk about the rest of the story here. And again, thank you to the organizers for the invitation, the opportunity to present this work in this context here. So, like Stelios, I'm just going to start off by very quickly thanking all the people in my group and all the collaborators that have worked with us since I started at UVic in 2019. A lot of names, so I won't list them all. Just to highlight the folks who are highlighted in blue on the slide here. These are the key players who have contributed to this specific project. So Jingjin Huang, who was one of my first PhD students, who has since graduated, was really the driving force behind our palladium chemistry efforts here. And both Ryan and Matt, who are now both in graduate school, were my first undergraduate students who really got this project up off the ground initially. So my group does a lot of work really sort of inspired and informed by my prior industrial experience. As Dr. Neha mentioned in the introduction, so I'm a former process chemist in the pharmaceutical industry. And so our work really spans synthetic methods development, catalyst development, and sort of tools development to enable high throughput experimentation and sort of data-rich experimentation in organic synthesis. So we have a lot of projects in a lot of different areas. So this slide is just sort of a bit of an introduction to the different areas that we work in. But really what I want to focus on is this DAB-PD-MAH complex that Stelios introduced that we developed as a tool to enable high throughput experimentation in a more reliable and robust way, not only for folks to be able to get better data for optimization and screening conditions for sort of end user applications, but also ultimately to inform things like building data sets for quantitative modeling, machine learning, predictive chemistry, which is another area that we're interested in, but also using it to develop new synthetic methods. And so as Stelios mentioned, the source of palladium that you use in a palladium catalyzed reaction is often very important to the success of the reaction. So we kind of came into this area more from the perspective of cross-coupling, so things like Suzuki-Maura reactions, Buckel-Hartwig reactions. I ran a lot of these when I was in process chemistry, and so anybody who's done palladium chemistry is probably well familiar with this set of the cast of characters in palladium coupling. You can run these reactions with everything from simple palladium salts like palladium dichloride or palladium acetate up to the much more advanced pre-catalysts, things like the Buchwald G1 to G6 type pre-catalysts, Hazari pre-catalysts, the Collicott and Nolan type pre-catalysts, the Oregon type pre-catalysts. Yeah, I'm listing off a lot of names here. This is a lot, very, very active area of research for quite a long time. One commonality to basically all of these catalysts is that they are palladium-2, palladium in the 2+ oxidation state. If you want to use palladium-0 as your precursor, up until recently, and there's some new work that's coming out of Scripps, Carrie Engel's group, that's also sort of tackling this area. Up until recently, the only option you have for palladium-0 is palladium DBA, the source that everybody sort of loves to hate. It works, but it can be unreliable. And there's a really great paper from Anenikov from 2011, organometallics, that kind of goes through a lot of the issues. Poor solubility, it's unstable in solution, different crystalline solvates give different reactivity, et cetera, et cetera, et cetera. And so as part of my love-hate relationship with palladium DBA, when we started the group at UVic, we wanted to make a palladium-0 source that was not going to have these issues. We wanted it to be solution stable. We wanted it to be soluble in a lot of organic solvents, easy to prepare, even to the point where I can go into the lab and make this. So the Weibo tile that you see here, that was actually me, the PI, getting into the lab. And so you know that a synthesis is robust when someone like me can get up from behind their desk and actually go run it. So we've made this on multi-gram scale. done a lot of characterization on the actual complex itself. And you can now, if you want, buy it. It's available from Sigma Aldrich. However, it's also readily synthesized from either palladium DBA or from palladium acetate. It's sort of a one day, two-pot procedure. And so again, our initial efforts in this area were informed by cross-coupling chemistry. And so I'm just going to go through a little sort of brief overview of some of the work that we did as part of this 2021 paper as it relates to the AAA chemistry that I'm going to come back to in a couple of slides here. So in addition to those features of the pre-catalyst like good stability, good solubility, easy to prepare, et cetera, et cetera, et cetera, really the key chemical property that we wanted, the reactivity property that we wanted for this complex is that we needed it to react rapidly and completely with basically any phosphine ligand, or really any ancillary ligand. We focused primarily on phosphines for this work, in order to generate a metallated palladium zero complex, again, very rapidly. And so the thinking behind this is that if you're running, say, a high throughput experimentation set of experiments, you're doing an in situ catalyst synthesis where you put the palladium source and the ligand into your small vial or well of your well plate. You need that thing to react very reliably. If you take palladium acetate and any one of these ligands, you might get 2 or 3 different species, and the rates of metallation may be different depending on the phosphine ligand. We're very fortunate in this case that this particular complex undergoes very rapid and reliable ligand substitution, where the alpha diimine, the DAB, from the pre-catalyst just gets displaced completely by pretty much every phosphine that we've thrown at it. This is just a series of different complexes that we've made. We can isolate these as well. They form in situ very reliably, but they're also stable in their own right. We've characterized a whole bunch of them. There's crystal structures of a few on the bottom. But I want to point out one really nice aspect about this complex is that not only are these metallations complete without an excess of phosphine, they're very rapid. And so the only ligand that we found that undergoes metallation slower than about, as fast as we can basically get down to the NMR spectrometer, is this tetramethyl T-butyl X-phos. And so the curve in green here just shows the ligand metallation progress over time. And so within about an hour at room temperature, this goes to completion. This is a very, very bulky ligand, huge cone angle, and it's known to be very difficult to metallate this to palladium-2, for example. In our case, within an hour, we get complete metallation. So this is the sort of extreme version of steric bulk that we're able to metallate with this precursor. So we did a whole series of high throughput experimentation and preparative scale synthesis for cross coupling with this precursor in the initial paper. And there's just one example that I want to highlight, just again as an intro to the AAA work. So we studied this imidazole and arylation reaction. This is known to be a pretty difficult reaction, known in the literature. We did high throughput screening to look for different ligands versus different palladium sources. Saw that our DAB PDMAH works well in a small scale screening context. However, when we take this reaction, we move it forward to preparative scale synthesis. What we see is that the yields drop off quite a bit. So a key difference between the screening scale and the prep scale here is we drop the palladium loading by about a factor of 10, because we don't want to run a prep scale reaction with 13 to 15% palladium. So a lot of these hits that we identified in our high throughput screening evaporated when running it on a larger scale. And so the in situ conditions on preparative scale, we're getting maximum about 40% yields, regardless of what we tried. It was only when we went to the preformed single component catalyst, this tetramethyl, again, the same bulky ligand, this tetramethyl T-butyl X-phos, single component palladium zero source, that now all of a sudden we get really good reactivity. And so this is, it indicates, again, as Stelios mentioned, it's not just AAA chemistry. A lot of palladium chemistry can be very capricious depending on how the reaction's set up, what the palladium source is, et cetera. And so as part of the collaboration, so after this paper came out, again, Stelios mentioned, he called me up and asked if the DAB catalyst could work for them. after that initial promising results in the natural product synthesis that he mentioned, we tackled a project to actually make those single component catalysts from our palladium source with chiral ligands for AAA chemistry. And so again, relying on this very rapid and complete metallation, we set out to make a series of single component chiral catalysts. So with the TROS type ligands that again Stelios introduced, we can isolate these palladium zero complexes in good yields, as well as phosphinoxazoline type precatalysts. But what's really, really cool is that we're able to get solid state molecular structures of several of these complexes as well. And so here, I'll come back to the naphthyl DAC in a second here, but we can now actually characterize in solid state as well as in solution these palladium zero complexes. And this again is a case of not necessarily being as intimately aware of the literature as I could be in the lead up to this. These are actually the first crystallographically characterized examples of these TROS type ligands that are bound to palladium zero in the way that they are proposed to in the catalytic cycle, both phosphines bound to palladium. Guy Lloyd-Jones's group has done a ton of fantastic work on all the solution properties of these kinds of complexes and all the various coordination modes that they can adopt, especially with palladium 2. And so again, by using this palladium MAH sort of scaffold, we're able to get stable complexes that we can actually characterize, which again is to our knowledge is the first time that people have been able to do this, despite the long history of the AAA reaction and the TROS ligands in particular. And so the eagle-eyed among you will have noticed that there are two different conformers between the naphthyl DAC and the phenylandin complexes here, the endo and exo conformer. And so just to talk a little bit about conformations, so this is a stereochemical model that was proposed by Guy Lloyd-Jones and collaborators in this seminal 2009 JACS paper cited at the bottom, where they propose that the NH bonds of the amides, as well as the carbonyl groups, are actually directly involved in helping to direct substrates in to the palladium center to help with stereo control. And so in particular on the top, that hydrogen bond between the NH and the allyl substrate, we observe in the naphthyl complex, this one conformer, the endo conformer, a hydrogen bond between that NH and the backbone and the maleic anhydride that's coordinated. So this is a model of that kind of intramolecular interaction. Now, obviously, maleic anhydride is not a substrate for AAA, and so this is again is a model, but it is again the first time we can actually directly observe this kind of hydrogen bonding in the complex. This isn't just a solid state effect. We can actually observe this directly in solution as well. And so with the sort of prototype phenyl DAC complex, using a combination of phosphorus and proton NMR spectroscopy, we can see evidence of this hydrogen bond and these two different conformers in solution. And so just as one quick example here, there's a pretty significant solvent dependence where in dichloromethane, we see a nearly one-to-one mixture of these two different conformers, whereas in THF, we see almost exclusively the exo conformer. And so we are still sort of thinking through this solvent effect to see if it is something that might help inform solvent selection for enantioselective reactions. And again, we're still sort of working through that. But again, having this sort of window into catalyst conformation as a function of things like solvent identity or other additives is pretty neat aspect of these systems. One other really nice aspect, and this is again another thing I wasn't intimately aware of, is that these complexes with standard sort of palladium sources are actually quite sensitive to oxidation. And so with palladium DBA, the line on the top here, if you just take palladium DBA, mix it with the TROS ligand under air, you almost immediately get formation of this PNNP palladium 2 oxidized sort of brick complex that's not catalytically active. And this is known in the literature, and the TROS group back in 1994 elucidated this. In our case, with the maleic anhydride stabilizing the palladium, we have a very stable complex. Even in solution under air, we see only about 20% oxidation within 48 hours. Much slower than the palladium DBA complex. And so what this means is that you can use these precatalysts just on the bench, no need for a glove box, and that's indeed how Stelios's group uses them in synthetic practice. Just because time is getting short here, I'll go through just very quickly some of the synthetic examples just to highlight the improvements and benefits of the single component pre-catalyst. Our Nature Communications paper has all the details. Basically, we can run through a whole gamut of different AAA reactions, and we can see that under sort of analogous conditions, you either get 0% yield with an equimolar amount of palladium DBA and the ligand, or with a single component pre-catalyst, you get 86% yield. Same thing here for another one of these reactions. If you use either DBA, palladium DBA, or allyl chloride dimer, that 1-to-1 ligand to palladium stoichiometry, the reactions are pretty poor, whereas with a single component catalyst, we get improved yields. Other AAA reactions, again, this top one here, we get consistent yields, fairly consistent yields throughout, but we find that with different palladium sources, we end up with different enantioselectivities. And the best enantioselectivity we observe, the most reliable set of reaction conditions, is using just a single component catalyst. And so we can get from 64% up to 81% E just by changing the speciation of palladium that we go in with. Another aspect of these reactions is often that you need to do premixing in order to sort of preform that catalyst if you're adding the palladium source and the ligand. We obviously don't need to do that with a single component catalyst, and so in this case here, we see again a pretty significant improvement in the yield going to that single component catalyst as opposed to the in situ formation. For these malonation reactions, again, this premixing effect. So if you use a sort of more elaborate premixing where you premix the palladium source and the ligand at 50 degrees, which is the standard procedure, you get really good yields and selectivities. But if you don't premix it at elevated temperature, if you just premix it at room temperature, which is sort of more typical in something like a high throughput screening protocol, you get a drop off in the yield. You're clearly not forming that catalyst as efficiently. Again, because we don't need to do any premixing, because it's a single component catalyst, just drop it in and you're able to get good yields. And again, we can see the same thing here with just slightly different conditions for doing this allylation reaction, where both the Fox type catalysts that we have work well just as single component catalysts. Finally, one of the starkest differences is in the butenolide type allylations that Stelios introduced in his part of the talk, where if we use standard conditions at 1 mol% catalyst for palladium DBA as a palladium source, we get very poor yields for these reactions, but a significant improvement in yield when we use that single component catalyst. And this holds true both for the sort of base generated enolate conditions as well as these decarboxyl allylation reactions, where it was really key to use the single component catalyst to get the reactions to actually work. And then finally, the last example here, because we've designed these complexes sort of from the outset to be amenable to microscale screening, high throughput screening, we took this allylation of a hydantoin derivative. This is not a reaction that had been known in the literature before, and applied our complexes to a pretty rapid optimization of this reaction. So using the DAB precursor as an in situ source, we're able to identify a suitable ligand to get acceptable yields and selectivities. Taking those conditions then forward into a next round of optimization using the single component pre-catalyst, we can do a sort of multivariate base and solvent array to find the optimal conditions. In this case, THF and sodium HMPS. Taking then that forward to a more targeted optimization for catalyst loading, temperature, and concentration, able to get up to 90% yield and nearly 90% E with about a 450 turnover number, so pretty low catalyst loading. And then finally, taking these conditions forward to a gram scale synthesis of this compound. So retaining that high yield and selectivity. And all of this is done in pretty short order because of the reliability and sort of user friendliness of these pre-catalysts. So that's it for me. Apologies for going a little bit deeper into the question and answer period, but again, I'd like to thank all the folks who contributed to this. Thank you to Stelios for kicking off this collaboration. It's been a lot of fun. and happy to take questions if we've got time.